Hey everyone! So maybe you are new to distributed systems, or you just need a quick summary before your upcoming job interview. In either case, in this video you'll find the most common concepts of system design and the most important aspects of them. So especially if you have an interview in the following days or weeks, I highly suggest you to watch the whole video because we'll cover things like horizontal versus vertical scaling, load balancing, microservice architecture, databases, including SQL versus NoSQL, replication, and sharding, as well as we'll walk through caching, CDN, and like event-based systems like message queues and PubSub kind of stuff. So I'll try to cover the most important aspects of them because it won't be like 5-10 hour long video, but if you need more information or more in-depth knowledge in some areas, or if you want another video which is diving deep into one of these topics only, just let me know in the comment section below and I'll try to just explain that concept more in detail. Alright, let's start with what is scaling. Let's say you have 300 users and you have an application running on this node. Let's call it node 1. You can also call it like host or a server. And these 300 users making call to this node 1. So at this point, everything might work as expected, and the hardware might be powerful enough to serve all these incoming requests. But what happens when you reach to, let's say, 600 users, or maybe 1000 or 2000 users? So at this point, you need to scale your system. So the initial hardware you have, maybe it's not good enough to serve like this many users. And at this point, you have two options. So first option is you still have node 1 here, but this time it's kind of more powerful. So based on your application and your needs, maybe you can double or triple the number of CPUs, or maybe you can double the memory. So whatever you need, you are just adding more powerful hardware to the same node, so you still have a single node, but more powerful. And this is what we call scaling up or vertical scaling. So the second approach is you have this node 1, which is the same one with the one here, and you are adding a node 2 here. Usually node 1 and node 2 are identical in terms of hardware. This type of scaling is what we call scaling out or horizontal scaling. Both have their advantages and disadvantages. For example, with scaling up or vertical scaling, it's easier to just add new hardware and you don't need to deal with all this additional complexity coming with the like scaling up or horizontal scaling, because if you have multiple nodes instead of one, it gives you ability to scale infinitely, but at the same time now you are dealing with all this additional complexity, how to distribute the load between these nodes and those kind of things. And another difference is most of the time, doubling the number of nodes is usually cheaper than doubling the hardware in a single node. And of course, as you can imagine, there's an upper limit for scaling up. So you can have only so many CPUs or so much memory, but at some point you'll hit the maximum. So if you want to scale infinitely or for like, let's say, millions of users, most of the time you'll need to scale horizontally. So most parts of your system, you'll need to scale out or scale horizontally. So that means you'll have multiple nodes for your service or your application. And then the question becomes, how do you utilize all of them and kind of distribute the load or the request among these machines or these nodes? So let's say for our service, we have 3 nodes. Node 1, node 2, and node 3. And on this side, you'll have your users using your application or your clients using your service. And then the question is, as we said, how do you distribute the incoming request to these nodes. So maybe again you have 600 users or clients, they are making call to your service. Let's say these nodes are for our booking service or maybe some application. So as we said, we need to decide how to distribute this incoming load to our nodes. And that concept is called load balancing. So let's call load balancing. And basically this is a box here. It can be a standalone node, or it can be just an algorithm or a program. Basically there are different approaches. For the time being, let's say users or clients are using this load balancing, and this load balancing will kind of decide which node to use. So there are three main load balancing types. First one is client-side load balancing. So in this one, this load balancing logic is living on the client side. So client being this one here. So it knows all the instances of the booking service, like all these three nodes, and it kind of decides which one to call. So one common approach is having a library rendered by the booking service, something like booking service client. And this client will know, so booking service has these three nodes, 1, 2, and 3, and it will know how to access them. Let's say booking1 abc.com, booking2 abc.com, and so on. And without involving anything else, the client will know and decide which one to call from here. Sometimes there might be an additional service here that booking client talks to get kind of this information, or it can be embedded in the client itself. So the second one is DNS load balancing. So if you are familiar with DNS concepts, usually when you type a URL to your browser, it talks to the DNS server and tries to get the IP address for that URL, and then just kind of accesses that IP address. And this load balancing technique is using the same concept. So let's say you have your DNS server here. So client is just saying call bookingabc.com to access our booking service. And when they type this URL or they use this URL, it will go to the DNS server. And since this service owner also owning this domain, they can just configure whatever they want. So for the booking.abc.com, they can say whenever somebody tries this URL, just return them one of these three IP addresses, IP1, IP2, IP3, and those are being IP addresses of these nodes. So DNS will just return randomly these IP addresses, and for example, for the first client, it might return IP1, and that client will talk to node 1. And for some other client, it might return node IP3, and that client will talk to node 3 in that case. And this way, you are kind of distributing the load between these nodes without using anything additional, just using how DNS works basically. So the third one is server-side load balancing. So in this one, you have a dedicated server just to do the load balancing. So in this case, the load balancer you see here, that's basically just another node or a bunch of nodes basically. And their only job is distributing the load. So they get a request from the user. So in this case, how it's configured is something like that. So client is trying to access order service.abc.com. So this time, this URL belongs to our load balancer node. So whenever somebody tries to access this address here, they are actually talking to our load balancer here, which is another node. And then after they get their request, so they're sending request here, which might have a JSON or something else. And this load balancer has incoming request, and now they also know all the existing nodes for the booking service, because actually in this case load balancer is part of our company or our application, and they are aware of each other. So load balancer knows which nodes exist, and it can just decide which one to send the request to. Server-side load balancing is one of the most commonly used load balancing technique because it gives better control, because all the requests are going through the load balancer host here. It has full information about incoming requests as well as number of nodes, how frequently or how much time it takes for each node to reply back. We have full picture of the whole system, so they can kind of distribute the load better. So one other advantage of using load balancer is preventing the single point of failure. So if you have a single node or two nodes, when they die or crash, basically you are out of nodes and you don't have enough node, or you don't have any node at all to serve the traffic. So in those cases, that's why you also use load balancers, so that you can kind of always have some nodes in that environment to serve those requests. And one of the common questions I get usually is, so now when we use server-side load balancer, most of the time it's a single node, then this load balancer here becoming the single point of failure. So how do we solve that problem? So the common approach for that is kind of combining second and third approaches here. So you have nodes and you have a load balancer which is distributing the traffic to those nodes. But this load balancer is not a single load balancer. It's more like you have multiple load balancers or multiple nodes, and they are using DNS load balancing. So which means when client makes a call, they might hit this load balancer or this one or this one or this one. So even if one of your load balancer crashes, you still have other hosts or other nodes that they can kind of balance the load and call one of these nodes. Now let's talk about common techniques or common algorithms used in the load balancing. So the first one is round robin. So in this one, so you have three nodes, let's say. So when you get a request, you send it to the first node here. When you get a second request, you send here. When you get a third request, you send to this one. And now when you get the fourth request, you start from scratch, this. So, and then basically you are distributing the tasks or requests to all nodes in the group in rotation or sequentially. So another one is list connection. So as I said, with the server-side load balancing, this load balancer here kind of has a connection between all these nodes and talking to all of them and aware of their health and everything. And it also knows how many connections each node has. So let's say this is serving to 5 users, this is serving to 10, this is serving to 1 only. So at that point, when a new request comes in, load balancer will say, okay, this has the least connection, and I should send this request to that, basically node 3 here. So the third one is least response time. So again, load balancer knows how long does it take for a single node to get the request and respond back. So it's, let's say you get the request from the user, send it to node 1 at time t1, and then at some point this node 1 is replying to load balancer, and load balancer returning this response back to the user at time t2. Let's say the difference between this is 1 second, but for this node maybe it's 5 seconds, and for this node, maybe for node 3, it's working on so many requests, it's taking 50 seconds to respond back to a single request. At that point, when a new request comes in, it will just say, okay, the node 1 replies in 1 second, so I should send this request to node 1. But at that point, node 1 become overwhelmed and now it might take 100 seconds to reply. At that point, when next request comes in, the load balancer will say, okay, let's send it to node 2 because it has the least response time. And the last one I'm going to cover here is source IP hash. So in this one, again, the load balancer is hashing the source IP. Let's say you have two clients. One is coming from IP1, another coming from IP2, and here is our load balancer. So when it gets a request from IP1, it will hash this IP and it will say, okay, for IP1, I'll send it to node 2, and it will send it to node 2 here. And when it gets a request from IP2, maybe it will send it to node 1. And now that it has this mapping here, whenever it gets a request from IP1, it will just send it to node 2 here based on the IP it hashed initially. So this is usually used for sticky sessions where you want to send same user to the same node, and this is mostly used because you might have a host level or node level caching, and you already kind of cache all the information about that user or the things they care in that host or in that node. So you don't want to send this user to some other node because then you need to make a call to database. You can't use the cache value on the host. So that's why sometimes you want to use sticky sessions, and source IP hash is used with that one. And these are all the techniques we want to cover in this load balancing section. So now that we learned scaling and load balancing, now let's move to the microservice architecture and learn the basics of this architecture. So if you are starting with a simple application, most likely you'll have a single service, and it might be a web application, and you'll basically expose some APIs or endpoints for your users or clients to use your service. And this will be more than enough initially. So let's say you are building an e-commerce application. So you'll need authorization and authentication, and you'll need kind of order management because people will be placing orders and you need to kind of manage all this order lifecycle. And once somebody kind of purchases something, then the fulfillment part comes in. And during all this process, you need to have some tracking capabilities because you need to track where the product is when somebody purchases something. And you also need notification systems because you need to notify customer when they purchase something, when you ship the product, those kind of things. When you invoice them, you need to notify the customer. And of course, you need kind of invoicing. And maybe at some point, you'll also have some advertisement components because you'll be getting advertisement from some other retailers or brand owners. So as you can see, there are many different aspects of a application. And once you start, most likely you won't have many features for each of these aspects. So it's fine to start with a single service and you'll have like a smaller features for each aspect in this single service. But as your application grows, most likely you'll have things like, let's say this is the order management bit, this is the fulfillment, this is tracking, this is notification, invoicing, advertisement. So this is a single service and there's no boundaries. It's a single, basically source code or code base. So people import from here to here, they call a method from here, they use here, it requires this one, this imports this one, and most likely you have a single database here. All the people, all the components are writing to and reading from. So at some point, everything will be quite messy. And another issue with this is, since you have a single code base, if you are changing something with tracking, you cannot just change tracking and deploy this small bit. You need to deploy the whole thing, which might cause some issues for this one here, which you wouldn't expect. So as your application grows, you'll need to kind of split this single service into multiple ones so that you can evolve them separately. So most likely you'll have a authentication authorization service here, kind of order management service here. So you'll have a fulfillment service. You'll have kind of tracking in a separate service, and let's say notification. So in this architecture, basically each part here is a standalone service, or we call basically these as microservices here, and they are kind of encapsulated. They own their own domain logic, their own models, and their own deployment, their own code base. So everything is separated. So the only thing they expose outside is an API, and they kind of communicate between each other based on this contract or based on this API. When somebody purchases something, you are creating an order, and now order service is calling fulfillment service to basically start the fulfillment process. And since you want to track this product, you'll most likely tracking service will call fulfillment as well as order management so that they can get updates on the product. And notification service might get information from tracking, order management, or if we have invoicing here, also from invoicing, because you need to send notification to the user or to the customer when tracking or invoicing kind of information changes. And that kind of sounds great, but you might be asking how these services know about each other. So usually you have something like service registry here, and basically all the services are registered against this one. This is kind of also another service. So it knows about all the services here. And basically by using the service registry, each service can know what other services exist in the environment and what, like how many nodes they have, how can I access to one of these services, what's the URL or endpoint for that, those kind of information. So what's the advantage of using this architecture? So let's say invoicing is, most of the time it's happening asynchronously and it's not time critical. You can even create an invoice 1 hour later. So for that reason, you might say, okay, I just need a single node or a single server for invoicing service, but order management might be getting a lot of requests from the users because when you purchase something, when you cancel your purchase, when you edit it, basically all those things are going to order management service, and it needs to kind of react to these requests fast. Maybe a user waiting on the other side on the UI and waiting for a response, whether purchase or update was successful or not. So for that reason, you might need maybe 4 nodes or maybe even more. And for tracking, maybe you need only 2. So this way you can scale your services separately based on the needs. So another advantage is, let's say you need to change something with invoicing. You can just, so basically invoicing has its own source code, its own code base. You can just make the change, deploy it to production, and you only need to deploy this single service. As long as the API or the contract between these two services are still valid, you didn't break anything. So they don't need to know we are changing something in invoicing as long as we keep the API backwards compatible. So this way you can just, each component, each service here might be owned by a separate team, scale separately, deploy separately. You can even, let's say now notification services using, let's say a SQL database, you can just deprecate that and move to a kind of NoSQL database, and it wouldn't be even visible to the other components as long as you do the migration properly. You can change your infrastructure, you can do whatever you want within your microservice, and it won't affect others if you do it properly. So the next question is how user or the client is kind of accessing all these services. So we have this user here, who is using our e-commerce website. One not very common approach is just letting them call these services. Basically, they can call order management service if they need some order information or purchase something new, or they can call invoicing service to get some invoice details, for example. But a more common approach is kind of hiding all this internal stuff and putting a gateway between our internal services, internal microservices, and the user. So user just talks to this gateway, and this gateway kind of knows how to talk to these internal systems. So user might send a request to orders to get all like list of orders belongs to him, and then gateway will call order service and then return the result back to the user. User might call invoices endpoint. So this gateway is usually it's just a kind of a thin web application layer. It's just talking to other microservices. So when they hit invoices endpoint, gateway will just talk to invoicing microservice and get the information needed. Gateway might also talk to multiple services to collect kind of an aggregate multiple information and return it back to the user. So in this approach, you can use HTTP REST kind of communication protocol here. And when you get the request, you can validate. You can call authorization authentication service to make sure user is authenticated properly. And after that point, gateway can just talk to other services. And internally, these services might use RPC or REST or kind of any other communication protocol. So it's all for this video. Thanks everyone for watching. We will cover the other topics in another video. If you have any comments or questions, just use the comment section below and stay tuned for more videos.